So, in the last lecture we saw that Irwin's formulation can give a parameter which can describe the stress intensity at the crack tip if you know the location, which is the distance from the crack tip, which is r, and if you know the angle, then you can calculate the stress, and you must also know how much stress is applied on the system. So, then that gives you the stress intensity factor, which is K, and K is usually sigma root pi A, where A is the crack length or half crack length and sigma is the stress applied. This will have, so now the thing is that this stress intensity factor can have a critical value. So, depending upon what is the crack length and how much stress you have applied, stress will have some value. So, and this apart from the application of stress and crack length, it also depends upon the geometry of the specimen. So, for instance, Griffith calculated everything on a plate where the crack was embedded in the system, right. So, it was a through crack which was inside the system, and then if you have if you remember, we drew something like this for Irwin's calculation, and that has a surface crack, and this two different types of crack. So, here the crack length will be this distance, which is half crack length A. In this case, you will have this distance equals 2A. Even then, if you calculate the stress intensity factor for constant value of stress and a constant value of A, even then you will get different amount of stress intensity factors. Yes. So, there is another factor which is associated, which depends upon the geometry and the crack, so crack geometry or the specimen geometry, and that factor we can include it here, but before we do that we must understand that this stress intensity factor can have varying value, and when there is a definite value beyond which, so you are applying certain amount of stress, okay. You are applying stress which you started probably let us say with a value of 5 megapascal, and then you kept on increasing this stress. When you reached 50 megapascal, then this crack started propagating in the plate. So, something happened at some critical value of stress, meaning that something happened at some critical value of stress intensity factor, right, because if you are changing the value of stress, then you are also changing the value of a stress intensity factor. Crack length is constant as long as crack is not growing, and therefore, with increment in stress you will be having a different value of stress intensity factor. Now, if you reach a constant, a critical stress intensity factor, then at that, what is that critical value of a stress intensity factor? That critical value is where the material gives up, where the material damage is so high at the crack tip that a crack has initiated and the initial crack can grow. That is the value of critical stress intensity factor. We will call that as fracture toughness. When we calculate this critical stress intensity factor in mode 1, then we call it K1C. This 1 sometimes is denoted as Roman value, and it may look like KIC, but it is K1C and it should never be pronounced as KIC. So, this symbol resembles the fracture toughness or the critical value of stress intensity factor. If you reach that value, a crack initiates in the system, and remember that it initiates, it does not propagate, and we will come to that point when we talk about the procedure of experimentally measuring the value of K1C for any type of material following the ASTM standard. So, before we go there and before we define how we calculate the crack initiation fracture toughness, we must understand that a crack initiates and then it propagates, and we are here interested in the initiation fracture toughness, which is K1C. The requirement of K1C is that the remote stresses must be defined by the theory of elasticity, because this equation has arrived from the theory of elasticity. Okay. So, this equation was calculated by Irwin with an assumption that the material is deforming elastically, although we have seen that if you plot the stress at the crack tip, the stress intensification is asymptotic. So, it reaches a value of infinity at the crack tip. That cannot happen in reality, and in reality it will get truncated at some value, and this truncated value usually is sigma naught, which is the yield strength of the material, beyond which if the stress increases, then the material starts deforming plastically. And this is the problem in the assumption of Irwin, that whenever plastic deformation starts, then these equations will not hold, and therefore, this parameter will lose its value. Therefore, it is important to have predominantly elastic deformation in the material if we are using this concept to calculate the fracture toughness in mode 1. In order to ensure that material is deforming elastically predominantly, it is always good to have plane strain condition, because we discussed in the last lecture also that in plane strain condition the material is under too much constraint, and in plane stress condition the plastic deformation is higher in comparison to the plane strain condition for the same amount of force applied on the same dimension of the specimen. Okay. So, the few things which we have to remember is that measurement of K1C has to have predominantly elastic deformation. Okay. Then second is that we have to ensure elastic deformation by using plane strain condition, and third one is that we have to ensure that we have to remember that it is initiation fracture toughness. That is one thing. Apart from that, we also have to remember that the effect of a specimen shape is important. So, as long as I write just K, it is sigma root pi a, but when I say it is K1C, then K1C is a material property. It is like yield strength, which is also a material property. So, for instance, for titanium alloy, let us say titanium 6 aluminum 4 vanadium, which is the space material. It is also used in naval application. It is also used in armor application. So, vehicle armors, and this material, if we take this material, then we can have a value of K1C for this material, which will be constant, which will not change. So, as long as you are testing this material, you will have same value of K1C, and therefore, it is a material property like density, like resistivity. That's it is a material property, although unlike resistivity, it changes with the dimension of the material, and that we will briefly see in the next page. So, this is before we talk about that what can bring change in K1C, this you must have understood so far that K1C is a material property. Okay. So, for a grade of steel or for any alloy system, once you know that that alloy is fixed, so the grade is fixed. So, for example, P91 steel will always have same yield strength at room temperature. So, of course, there are some parameters which if you change that, these properties will change. So, if you change the temperature, yield strength will change, that we have already discussed and learned. If you change the strain rate, then the yield strength will change. Okay. So, these are the parameters which will be bringing change in the yield strength, but if you fix the temperature and the strain rate, then yield strength is not going to change as long as you are testing P91 steel. Okay. There will be some size effect, but that size effect is not very significant unless your size effect is too significant. So, of course, if you measure the tensile strength, it is again another discussion how to measure the tensile strength for a very small size of P91 steel or any other material. So, for instance, in micrometer size, if you are making a specimen, then of course, that material property will be different, especially in brittle materials it happens. Like for example, if you test the yield strength or flexural strength, which is the strength in bending for graphite for example, and you do that testing in situ in the electron microscopy. So, you make a cantilever type of a specimen of graphite in the electron microscope, and this specimen is in the micrometer size. The size of this specimen is very small. So, if from this specimen if you find out any material property, that could be different from what you get from a bulk specimen. So, in the millimeter range or bigger than that. Especially in the brittle materials, the property has a lot of side effect inherent in them, and that we have also discussed with the experiment of Leonardo da Vinci. So, but keeping that aside, we will not have any change in the yield strength as long as we are testing at room temperature at the constant strain rate for P91 grade of steel, and that will be true also for K1C. So, K1C is a material property, but this apart from temperature and strain rate, it will have an effect of the thickness of the specimen, which is usually represented in fracture mechanics by the symbol B. So, B represents the thickness, and as you increase the thickness, you are going from plane stress to plane strain condition. So, this K1C value shows a pattern here which looks like this. So, in many books you will find only till here. So, you will see that, and so this region belongs to plane stress domain. So, this region belongs to plane stress, and beyond this you have plane strain condition. So, in plane strain condition you will have constant value of K1C. So, once you are in the plane strain region, you can keep on increasing the thickness, there will be no effect on this value. So, it becomes a material property in plane strain condition only, and therefore, it is important to assure that the specimen is in plane strain condition when you are trying to measure this property, which is fracture toughness, and this is called plane strain fracture toughness. Okay. So, if you remember, we calculated that the plastic zone radius in Irwin's approximation, and this also was proposed by Irwin, is some constant value into K1C. So, it was K by sigma naught whole square, but you can calculate it by, because if you are trying to measure K1C, you will be reaching to that critical value for sure. So, some constant into K1C by sigma naught whole square. This constant value will be 1 by 2 pi for plane stress and 1 by 6 pi K by sigma naught K1C by sigma naught whole square in plane strain condition. So, you see that in plane strain condition the plastic zone size is smaller, and in plane stress it is higher. So, that means in plane stress you have a larger area which is going under the plastic deformation. So, we need to ensure, if we have to do this testing, we need to ensure that this plastic zone is very, very small. If not, then it was proposed by Irwin that what happens if you have some amount of plasticity, because it was not possible to ignore plastic deformation, because we are not dealing in the era of Irwin and after that. So, 1920s and after that, I think 1920 was Griffith, so it should be 1940 when Irwin proposed. So, 1940 to 1967. So, 1940 already we are in World War II era, where a lot of development has already happened, and steel is already a material which was used in those days in almost many war applications. So, it was not possible to ignore the plastic deformation of the material. So, therefore, you have some amount of plastic zone here at the crack tip. Okay. What happens when there is a plasticity? What Irwin said that it is, so what happens is that this crack tip will blunt. So, initially we have a sharp crack tip, and this is also another important point. Apart from, so the conditions for measuring the plane strain fracture toughness is that you must be in plane strain condition. So, you should have significant amount of thickness of the specimen. Okay. So, that is our condition. Apart from that, another condition which fracture mechanics puts forward is that the crack has to be sharp, and we will come back to this point, because the calculations by Irwin was done for a sharp crack. So, this formula which describes the stress in this form, which was apart from Irwin, it was also calculated by Williams and other researchers. So, here the assumption is that the crack tip is very sharp, and so we will come to that part also, that how a sharp crack tip is made when we test the specimen. But before that, if there is some amount of plastic deformation in the material, then what can we do about it? So, when the material deforms plastically, you are applying some stress here and you are trying to open it. Okay. So, what happens after some time is that this crack opens up and it blunts. So, it opens up like this and it has some amount of blunting. This blunting is because of plastic deformation. If it is just elastic and then there is no strength in the material, then this blunting will not appear. This blunting happens because of the plastic deformation. So, what Irwin proposed is that you can extrapolate this crack. Okay. You can imagine that the crack tip has shifted a little bit ahead, okay, and beyond that it is still elastic. So, what Irwin proposed is that if there is some amount of plastic deformation and you have some amount of blunting, then you can imagine that the initial crack length has actually grown. In reality, there is no crack growth, there is just blunting, but you can imagine that the crack which had a length initially of A has now grown to a different length, which is A dash, for instance, and this A dash, Irwin said, must be equal to the initial crack length plus the radius of plastic zone. So, you can, but this will also be valid only when this plastic zone is very small. It will be causing different problems if the plastic deformation is too high. Okay? If the plastic zone radius is very large, then this virtual crack growth cannot be imagined or assumed, and we will discuss this part also at a later point of time, but at this point of time it is important that you can consider that the crack has virtually grown to by an extra amount of Rp, and then that is your initial crack length. So, if you calculate fracture toughness, which is equal to alpha, which is a factor of shape of the crack, we will discuss that part also, into sigma root pi a, and then there is some plastic deformation. So, then you can put this value. So, you have this value, right, you have calculated, you have applied some amount of stress, you had some amount of A, then rest of the things are known to you. So, you can calculate K1C. Okay. So, of course, this sigma will be sigma c at which you define the fracture toughness, and you must have some amount of plastic zone radius also, which you can calculate from this. So, then what you can do is you can say that this whatever value you got from this formula is equal to alpha sigma c root over pi a plus Rp. Okay. So, from this, so you get the value of K1C from here, you put this here, and this Rp you again calculate from K1C, right. So, this Rp is coming from, so let us say, let me go to the next page to explain this. So, Rp we are so let us say that first we calculated K1C from sigma root over pi a, which is the initial value of the. So, this is the critical value, then you of course have the shape factor, which is alpha, and then you have a. So, you have K1C value. Now, let us say that this is initially, okay. So, this is I. Then I calculate the plastic zone radius equals to 1 by 6 pi. So, I am taking plane strain condition K1C, which is I divided by sigma naught whole square. Now, I use this value in order to calculate my K1C I plus 1, which is equal to alpha sigma c root over pi a plus Rp I. Now, I do the same thing to calculate Rp I plus 1. I use this Rp I plus 1 back and I calculate K1C I plus 2. Okay. So, you remember this equation and this equation So, this is basically that equation. So, these two equations are being repeated and we are following an iteration, okay. And we do this until the difference between K1C I plus 1 minus K1C I is very small. So, equals to let us say 10 to the power minus 6 or so. So, when these two values converge, then we say that we have found our value of fracture toughness. Okay. So, this was proposed by Irwin to accommodate some amount of ductility, because we cannot avoid ductility, we cannot have a material which is completely we can have material which is completely brittle, but we do not want to use those kind of material. We want to have some amount of toughness in our material, and for that we cannot be, our calculation cannot be based on completely on theory of elasticity. So, how can we avoid the disturbances coming because of the plastic deformation and still use the theory of plasticity? So, if my plastic zone is considerably small, we can play around and do this so that we can find out the fracture toughness.